I should have done that earlier. I actually totally forgot about that. Since I had it all set up like hours ago.
I've got this one.
Yep. You need to send Brendan a link, like YouTube link or anything.
I think I can.
How do I do that?
You have, yeah, it would be under links. Video.
Alright.
So you can take it.
Thank you. How do I get rid of that? There we go. Hey Angela, are you done? Are you finished?
Yeah, my last 20 minutes.
Is that good or bad?
It's fine.
Cool.
I did a great job.
Alien Worlds after office hours. We're just starting now. Are you like taking off?
I'm leaving that today. Dang it.
Oh, good. You told me. You told me. Oh, nice. Are you around like for the next hour or?
Yeah.
Sweet. Just an hour. No one else is around yet, but I am actually recording. That's fine. It's sort of like what a professor does. All right, we're online now and ready for the 4th office hours for Alien Worlds. I'm here with Leanne, and Brandon's at home. He's going to be monitoring from afar, and will be sending me various questions. Hopefully those of you who are wanting to link in have got the Google Hangouts or YouTube's links and can look in, and some of you will be just watching this ex post facto, as we say. We'll start. We have a bunch of different questions that people have posted from the web, and Leanne will feed those to me, and I think we can begin because we have a bunch of them.
All right. First one is, would there be changes in weather on a tidally locked planet?
Oh, that's a really cool question. So the question is, would there be weather or different weather on a tidally locked planet? So let me explain what that is. Especially if we had, for example, a really low mass star, like a low mass M dwarf, and we wanted to have a planet that was in the habitable zone of that star, so that we could have liquid water on the surface. We might actually have to bring that planet close to the star because that star is cooler, less luminous, and so the habitable zone is much closer. On the very lowest mass stars, that actually is so close that the tides from that star won't allow the planet to rotate anymore, just like, remember, the moon going around the Earth. We talked about this, I think, during the last office hours. And so that planet actually won't rotate anymore. The same side of the planet will face the star. We would call that tidally locked, or a geosynchronous orbit. And so what that means, of course, is that the one side of the planet will always be lit by the star, and the other side will actually be always dark. And again, I think I said last time, you can imagine some really cool sci-fi story or something where you have people who live maybe right on the edge, right on the Terminator, where in daytime you could walk across for day and you could walk across at night. You kind of set your own hours by how you wanted to cross the Terminator. But certainly that we do think that might make some very interesting weather patterns. You would be always heating exactly the same spot on the planet. And so weather would be very different than it proceeds on Earth, where you're constantly heating different places on the Earth, both daily in what we call diurnal pattern, but also seasonally. So as the Earth, because of Earth's tilt as it goes around the sun, different latitudes are heated differently. And that's actually really the reason why we get warmer weathers in the winter or the summer and cooler weather in the winter, is just that latitudinal change. But we're constantly heating different locations on the Earth on a daily basis. And of course, on an exoplanet that was tidally locked, you would constantly be heating the same place. That doesn't mean that some of that heat wouldn't transfer to even the dark side of the planet, because you actually could still have winds, and you could have weather that takes some of that heat and redistributes it across the country, across the planet. And actually, we have some evidence from at least massive planets that we think are tidally locked, where there is actually some evidence of weather transporting heat. That's something we actually already know about, based on some infrared observations of exoplanets. So we have some evidence already that there is heat transfer that happens in tidally locked planets. But the weather would still be very different. You would literally have one place on the planet that would just be constantly bombarded by starlight. And so that would be very, very hot. And you would be able to redistribute some of that heat through winds and clouds and things like that. And there would definitely be part of the star that would, or the planet, that would always be very, very cold, because it would never see light, and it would be very hard to transfer the heat all the way from that one side all the way to the other. So yes, weather would be very different. Again, I think in the reality, I think probably you would want to have people living, if you had life, you probably live right at the terminator, where you could cross between night and day, kind of make your own nighttime and daytime.
Okay. Now we have if you were sunbathing on an exoplanet around an M dwarf, would you still need sunscreen due to the lower?
So a related question that's actually kind of cool. If you were sunbathing on an exoplanet, let's say on a wonderful habitable exoplanet filled with lakes or oceans, around an M dwarf, which gives off way less light in the ultraviolet, would you have to wear sunscreen? And certainly low-mass stars are cooler, and most of their light is peaked in the red optical or even the infrared part, unlike our sun, which most of its light appears in the optical or visible part of the spectrum. And because of that, the typical output of a really low-mass star, an M dwarf, is very low in the ultraviolet. Actually, so low that you probably would not have to wear sunscreen in the same way that you have to around a star like our sun, why we all put on sunscreen when we go out in the summer. That said, when M dwarfs are really young, when the M dwarfs are really young, they actually put out a huge amount of high energy radiation. It can actually be ultraviolet, it can be X-ray, and so if you're sunbathing around a young M dwarf, you actually probably have to put on even more sunscreen than you do on the Earth. So it's actually a kind of complicated question. It's an old M dwarf that has kind of ceased its what we call magnetic activity, its flaring, stuff like that. Then you're probably fine going out without any sunscreen. But if it's a young M dwarf, you probably have to coat your body or wear even a suit or something, because the amount of high energy radiation will actually exceed that of the sun. You have to also remember that if you're a habitable planet around an M dwarf, you're considerably closer than we are at the Earth. I mean 10 times closer. So even if the M dwarf had, let's just say, the same amount of UV radiation, that means because you're 10 times closer, you're exposed to 100 times more flux of the star. And so you actually have to worry about that fact that you're much, much closer to the star, just because it's putting off less heat and less energy. And so the habitable zone where you can be sunbathing, at least around an ocean or something, is much closer.
Will the planets in our solar system ever align? And if so, what?
So will the planets in our solar system ever align? We actually had to look up the real answer for this. About every 500 years, or so. So it will be a long time before all of the planets align. But a very interesting sub-question within that is just say the outer planets, Jupiter, Saturn, Uranus, and Neptune. Those actually aligned pretty close in the 1980s. And one of the reasons that the Voyager spacecrafts were sent out when they were was that it allowed us to actually send a probe that would, instead of visiting one planet, would visit all four of the outer planets, although at that time Pluto was a planet, so it's four of the five. But it worked out well that it went to all four planets. And that's because they were aligned. And that alignment of the outer planets happens about every 176 or every roughly 200 years. So that won't happen again in any of our lifetimes. And then the full planet alignment takes even longer for you to make sure you get every single planet all perfect and aligned. So a very long time. And it really doesn't mean anything. It doesn't mean anything gravitationally. It doesn't mean anything certainly astrologically. And it certainly, but certainly in the 1980s, it was extremely useful because it allowed us to send probes out that could actually visit multiple worlds in one mission.
Is an ozone layer necessary for habitability, and do we observe them already?
Oh, cool. Is an ozone layer necessary for habitability, and do we observe those on other worlds? I'll actually answer the latter question yet first. We have not observed an ozone layer on other worlds yet. Ozone is O3. It's a very complicated oxygen molecule. And oxygen alone on the surface of the Earth is actually a sign of life. Almost every single bit of oxygen that we have here on Earth is due to life, mostly from photosynthetic materials, either bacteria or plankton or plant life, which breathes in carbon dioxide and give that oxygen. Some of that oxygen is allowed to combine with other oxygen to make things like ozone. And as many of us have heard in the news over the last several decades, the ozone layer is actually important because the molecule ozone is very, very difficult for UV light to penetrate. It absorbs a huge amount of ultraviolet light. And so it ends up protecting us. It's like a bit of a sunscreen for us. Is that essential for life? It would certainly be essential for you and me to live comfortably on a planet orbiting a sun like our own, or certainly a hotter sun, or maybe, as we said earlier, an active low-mass star. But, I also have this sense that life is very resilient, and if you didn't have a strong ozone layer, life developing on our world would probably figure out a way to become accustomed to high levels of ultraviolet light. And to be honest, some of the reason UV is bad is that it disrupts our cells. It can cause skin cancer, which is really just disrupting the patterns of our cells. And some of that high energy radiation may be really important for mutations that speed up evolution. One can imagine important scenarios for having that. But I also really think that based on the evidence we see here on Earth for life, that life elsewhere in the galaxy is probably extremely resilient, and that if it's in an environment where it's very UV heavy, my guess is life will figure out how to live in that scenario. So yes, it would be important for you and me, and some other life forms that we have here on Earth, but it may not be essential for habitability as we know.
Does UV penetrate water? Like, is it affecting life at the bottom of the ocean?
Oh, good question. Leanne asked, does UV penetrate water? It's actually very hard for UV to penetrate water, especially vast amounts of it. It's actually hard for most high-energy radiation or high-energy particles to penetrate water at any appreciable depth. And so the UV radiation that hits the Earth's oceans doesn't penetrate. I mean, eventually, by the time you get to the sea floor, even shallow sea, there's almost no water. If you've ever been diving or even scuba snorkeled and jumped down a little bit, you notice it gets dark very quickly That's just because even the optical light can only penetrate a certain amount of depth. In the UV, it's even harder to penetrate, and actually infrared, it's even harder. Water actually is an enormous absorber of infrared light, which is why it's a greenhouse gas. And so, yeah, this wouldn't affect life in the oceans almost at all.
I know that light started.
Sure, that's right. So yeah, if you had life starting in the oceans, or maybe even you have exoplanets where all of the life is still in the ocean. Or what?
There's all ocean.
Or there's all ocean, which is totally a possibility. It's a total water world. All of those are possible. Cool.
Did you want to do the assessment questions now, or
let's do those at the end.
Okay.
Yeah.
Why are radial velocity curves not symmetric around zero?
Oh, why are radial velocity curves not symmetric about zero? It's a cool question. So I think we've hopefully shown enough good examples of real data or made assessment problems that were mostly realistic to show you that when we do the radial velocity curves, it doesn't always have a perfect, the midpoint of the sinusoid is not necessarily right at zero. Let me show you that. I think you can see the board. Oh yeah, perfectly. You can see my oh, you can only see the saddles of my bikes. That's good. Yeah, so if I have a radial velocity curve that's something like this, and I draw a line kind of right through the center, the question is, this line is not always at zero. So in this case, I've written maybe 20 meters per second. But it really can be any value. And the question is, why is that not perfectly zero? And that's because stars actually have their own motions through the galaxy. They are not stationary from our perspective. Even our own sun is whizzing around the Milky Way at roughly 200 kilometers per second, 210 or so kilometers per second. Most stars in the disk whiz around about 220 kilometers per second. And our star is actually moving a little bit slower than that, turns out, for a variety of reasons. And stars move in all sorts of random motions, depending on things of like how they formed and what their ages are, things like that. In fact, one of the things that my research group studies and works on very carefully is looking at the motions of stars as they move around the galaxy. And so it's very rare to find a star that's moving with no motion towards or away from us. And so that's the reason when we were looking for exoplanets via the radial velocity method, we're looking for that wobble that's about the star's typical motion through the galaxy. And again, almost all stars have some motion through the galaxy. Cool, really, really cool question.
Okay, we make direct observations of stars at different wavelengths. Do we also make observations for radial velocity and transit at different wavelengths?
Yes. So the question was, do we make observations direct observations of exoplanets at different wavelengths? Do we do the same at radial velocity and using the radial velocity and transit methods? I'll answer the first question first because that's probably the easiest one. Most of the radial velocity measurements have been done in the optical or visible. That's mostly just a techniques and tools reason. The technology has been such that our highest quality spectrographs that can get very precise measurements of a star's motion towards us and away from us, most of the instruments that can do that have been in the optical part of the wavelength. There are a few new instruments that can do that just into the infrared, which of course is better for stars like M dwarfs or cool stars that emit most of their light in the infrared. It turns out through a property of optics, the longer wavelength you go, the less precise both images and spectroscopy you get without actually improving your technology. And so you actually have to work harder as you go to those longer wavelengths. But there are some new instruments that are actually being able to do radial velocity detection in the infrared. But almost all of it has been in the optical. And that's really just a technology constraint. For transits, actually, it's totally different. Transit detections have been made in X-ray, in ultraviolet, in optical, in infrared. I am not aware of a radio one, but in principle, it very well could be made. That and actually, although we didn't talk about it in this course, one of the interesting things you can do with the transit method by looking at different wavelengths is it turns out stars have actually different sizes at different wavelengths. Our own star has a different size in the X-ray or the UV versus the optical because of the light that the star outputs that actually comes from different layers of the star. And so both the star has different size, but actually the planet can have a different size based on its atmosphere. Where the light is allowed to go through the atmosphere of the planet changes as a function of wavelength. And so by probing the transit method at different wavelengths, you can actually probe whether or not the planet has an atmosphere, for example. And so people have done that very carefully. And so they've been able to actually demonstrate without doing any spectroscopy, without looking for the specific gas features in a planet's atmosphere, they've been able to demonstrate that exoplanets have atmospheres by looking how different wavelengths of light pass through the star's atmosphere and show that the planet has, you get a different transit depth as a function of wavelength, which of course if you just had a big ball of rock, you wouldn't actually, it would always block the same percentage of light from the star. But if you can actually demonstrate that as you change wavelengths, that size of that planet changes, that must tell you you're looking through gas that's able to absorb different wavelengths of light to a different depth. And so it's a really clever technique that, yes, people are using quite a lot to help characterize exoplanets. And it's certainly much easier than taking a spectrum of an exoplanet.
Do we reduce our data with techniques like Fourier transforms for the transit and radial velocity methods, or do we use the broad data?
So question was, do we use a method called Fourier transforms to reduce our data either in the transit detections or the radial velocities or both? And I'll answer that, I guess, in two pieces. Well, first let me explain for those of you who are watching who hear Fourier transform and go, wow, what the heck is that? Fourier transform is a mathematical tool that allows us to look at things that repeat over and over, like similar to the graph, the radial velocity graph that you can see right behind me. That's something that would repeat over and over again, and it has a set amplitude, the height of the wobble, and it has a set period. And so one could imagine that I could express that mathematically by just a single line that says that has one period of some height or some power, right? So rather than write a graph that has to have to repeat over and over and over again, as it repeats over and over again, that takes up a lot of room, whereas I could express that same thing as a single line at a given period. So for things like the radial velocity method, the answer is yes. Like, one of the techniques that's used to try to pull out periodic signals, things that happen over again, like a wobble, is actually used. There are other techniques we do as well. People will actually model all sorts of fake planets and compare them basically to the data, and they see what matches the best. And so you make up a lot of different fake planets and you compare it to like the signal, and then you actually see what's modeled the best by the data. That's actually probably the most prevalent method, but certainly things like this periodic signal is used. Transit method is actually not that. Most of the time people look at raw data, or again, they model what a transiting planet might look like and compare that to the data. Transits can be harder to do via like Fourier transform because it's not as repetitive. I mean, certainly you get a transit signal every time the planet comes back around, but again, remember, for something like the planet Jupiter around the sun, that's going to happen once every 12 years. And so the periodic signal only happens briefly once, and then you have a lot of time in between. And one of the things that you do with transit data, say from like Kepler, where you might use something like this Fourier transform mathematics, is actually looking at the rotation of the star. which has nothing necessarily to do with the planets themselves. But it turns out that the planet rotation actually happens, or sorry, star rotation happens. So the fastest stars rotate, I don't know, actually every few hours they go through rotation, to the slowest stars, which are, maybe take a month to go around. But we can see that signal very clearly when we do a Fourier transform on, say, the Kepler data. And so lots of people are working on that. Leanne says I'm frozen to her on her computer, so we're making sure that it's not frozen for everyone. Could be a wireless issue here. I'm still fine, it looks like. All right, looks like we're all good. So we will continue with the office hour. All right.
We've got some questions about the migrations of the outer planets.
Sure.
What caused them, and did they start inside or outside?
Oh, good question. So 2 questions related to planet migration. One is what causes planets to migrate in the first place, and the other one is did the large planets, particularly in our solar system, did they start outside the frost line or inside the frost line? So let me start with the second question first. And to our knowledge, we still have no way of building large planets unless they form beyond the frost line. That we need to have planets have access to things like rock, iron, and more importantly, ice. When you have all 3 of those building blocks, you can now build really big planets. And so planets like Jupiter, like Saturn, they had to have formed of rock, iron, and ice. A core that was probably something like 10 to 15 times the mass of Earth. Sorry, we have a phone call in my office that Leanne's going to answer. But when you actually have when you have a 15 mass Earth, it can now actually begin to hold on to the gravity that, or it can have the gravity that will be able to hold on to all of the hydrogen gas, like Jupiter does. So Jupiter had enough mass and enough gravity to hold on to all the hydrogen gas. Oh, I'm sure they knew it was.
They asked me to be your officer and told me in the vote and they responded that I have the wrong number.
Oh, okay. Weird. So that's the reason why we think all of those large planets were formed outside of the frost line. In our own solar system, that's about at 3 astronomical units. But around a much larger star, that would be farther away, and around a much smaller star, that would be much closer. The other question was, how does this migration happen? We think, again, that even in our own solar system, Saturn and Jupiter likely migrated a lot early on. Certainly, we've seen in this class that things like the hot Jupiters, these first exoplanets that were found via the radial velocity method, were identified as Jupiter mass objects that are really close to those stars. And again, we don't think you can form those where those are now, that you have to form those beyond the frost line, beyond the snow line. They have to migrate in. The way the migration happens is actually the planets interacting with the disk of material, and the actual planets can exchange things like angular momentum, this physical quantity that allows for rotation of material. They can exchange some of that with the gas in the disk. And it turns out that exchange allows the planets to actually change their orbits. And so that can actually it can actually allow the planets to actually move in, or to be honest, move out as well. And this has actually been shown for decades now in simulations that it's actually very easy. If you just set up a gaseous disk with planets in it, the planets will actually begin to remove some of the gas via their gravity. And when that happens, the planet may interact with gas that's moving a little faster than it on the inside, and that has allowed to actually like exchange some angular momentum and make the planet actually move in, or it can actually do the opposite. It can move on the, it can exchange gas with this gas on the outer side, where it's moving slower. And if you, as long as you have the gas still present in that disk, that gas can actually affect the planet's orbit. Once the gas goes away, at least that primary migration method actually disappears. There's some other ways you can actually have planets migrate actually through interactions with other planets. We think that does actually probably happen in some cases, but it's probably not the primary mode of migration, and certainly probably did not happen, at least prevalently, in our own solar system. Most of it was probably due to interactions with the gas disk. Gas disk, remember, lasts about probably at most 10 million years for at least a star like our Sun. And so at the end of 10 million years, everything's pretty frozen in. But early on, you could get a lot of stuff moving around. And again, we think that Jupiter and Saturn actually migrated way in, and that actually explains some of the sizes of the planets that we have. In fact, the small size of Mars is likely due to the fact that Jupiter and Saturn, Jupiter in particular, migrated very close to where Mars is forming. Mars actually should be much larger than the Earth, which would have cool ramifications for habitability, because it means Mars probably would have had enough gravity to hold on to a much larger atmosphere. Mars had access to probably even maybe the beginnings of some ices, but certainly a lot more rock than it did now. But it doesn't. It probably wasn't allowed to get as big because Jupiter migrated in and got really close to it, and basically kind of stole away a lot of the material that would have gone into forming Mars. So it actually has had pretty huge ramifications for our own solar system. Even though we don't have hot Jupiters, planet migration really likely is the reason that our solar system and the planets in our solar system look the way they do.
Could a high-gravity object destabilize the Oort cloud and then comet into the interstellar system?
Super cool question.
Is there anything like that around?
I remember seeing this. This is really cool. So we talked, I think we've talked only a tiny bit about this entity called the Oort cloud, which is really the last bit of our solar system at all. It is tens of thousands of astronomical units away from the sun, so really far out there. It's really essentially in interstellar space, to be honest. You've left totally any effect that the sun has ends at about 100, maybe 120 astronomical units, right about where Voyager is. Voyager has kind of crossed into interstellar space. But it turns out the sun's gravity still plays a little bit of a role for objects beyond that. And so there are comets and objects that were likely flung out of the solar system early on by things like Jupiter when it was migrating, or Neptune or other things. They were flung way out of the solar system to, tens of thousands of astronomical units in some cases, in a actually pretty spherically symmetric direction. So not just in a disk, but actually almost a sphere that surrounds the solar system, and that's called the Oort cloud. And it's actually where a lot of the comets that we see in the night sky come from. They come from these very vast distances. And so the question is, you have all of these comets that are out here at 20,000 or more astronomical units. They're on orbits that are extremely elliptical, so that they essentially got shot out of the solar system, and they actually almost take a straight line back. They're so elliptical. But that means, again, if you remember our Kepler's laws, you remember that closer, faster, farther, slower. And so when they're close into the solar system, when they're going through their cometary phase and these beautiful long tails, they're moving very quickly. But when they're far away, they are actually really they're really they're really moving slowly, and so they end up spending a huge amount of time out in that outer part of the solar system. And so they actually form this cloud around the solar system that we call the Oort cloud. The question was, if you have this Oort cloud that's made up of really likely thousands, if not tens or hundreds of thousands of objects, or is there another nearby massive object, be another star, a massive planet, something like that will disrupt those objects and maybe send them raining down into the solar system? Well, we don't know of a, say, companion to the sun, let's say, or something like that. As far as we know, the sun is a single star. It's not a binary star or something. However, there are billions, hundreds of billions of other stars in the galaxy, and as we said earlier in the office hour, the sun is moving, at hundreds of kilometers per second through the galaxy. So once in a while, it actually encounters another star, and so you can actually go through a pretty easy calculation. If you say that roughly there are a star every parsec or something, every few light years spaced throughout the galaxy. You can actually go through a calculation to figure out about how quickly or how regularly the star should encounter another star. And it turns out that happens about roughly every 100 million years or so, give or take a little bit, depending on what exact value you use. But about every 100 million years, which turns out is about one orbit around the galaxy, the sun actually passes pretty close to another star. And it turns out that time scale, about 100 million years or so, is the time scale for large extinction events on the Earth. It turns out, and we think that a lot of those large extinction events, at least the last two, one about 65 million years ago, and another one about 200 million years ago, were caused by large impacts. And so it is maybe not a total coincidence that every roughly 100 million years or so, the sun passes near a large star, and that large star could disrupt comets in the Oort cloud and could send some of that material raining back down into the solar system and cause, at least on the Earth, potentially large extinction events. That is not a total coincidence. It's actually a problem that I give to some of my graduate students as a good little just kind of order of magnitude problem. I actually think I wrote a comprehensive exam problem that actually has that exact answer in the end, that I wanted them to think about the extinction events on the Earth and the size of the Oort cloud. So, yeah. Yeah, so yeah, I'm sure they appreciated that. So that's a really cool question.
As a follow-up, what would the time delay be between encountering the object and things hitting you?
Oh, so the question is, what's the time delay between, passing, say, by a near star that would disrupt gravitationally upset affect the Oort cloud orbits, and actually having that planet or having that object, whatever it is, comet, come and hit, say, the Earth or come into the inner solar system? That's likely tens of years. So time delay of tens of years. I mean, it takes, and it would depend on the exact speed and the exact trajectory, but it takes tens of years at really fast speeds to get, it may be even as long as a century to get all the way out of the Oort cloud. So yeah, it can take a long time. But small on the astronomical scale, large on the human scale. We certainly would have time if we knew about it, but of course these objects are pretty small, and we've actually never observed an Oort cloud object in situ. So we've actually not ever seen an Oort cloud out at, again, they're out at 20,000 AU, which if you have a tiny comet-sized object is actually just about impossible to view from out that far. So we've seen things from the Kuiper Belt object, which is objects around where Pluto and Neptune are. But we've actually never observed objects out at 20,000 AU. Now, of course, we've observed comets that we can trace their orbits back to tens of thousands of AU. So we know exactly where they came from, but we observe them when they're much closer, and by carefully tracking their motions, we can figure out exactly from where they came. But we've never actually seen them out at those distances.
Okay. Do we think that asteroid belts are common in other planetary systems?
Do we think asteroid belts are common in planetary systems? They likely should be fairly common. I mean, not necessarily in the same extent as ours. Ours are our main asteroid belt, which is this region between Mars and Jupiter, is really a planet that never formed. Again, there was enough material between Mars and Jupiter to form a whole other planet, probably a very large terrestrial world, maybe even larger than the Earth in many cases. Actually, probably larger than Earth because it would have certainly had access to ice because that's right around where the frost and snow line is in our solar system. But again, Jupiter played this huge role in that Jupiter really didn't allow something to form there. It disrupted it through a variety of gravitational instabilities. Didn't allow there to be a planet there. And so probably any system that you have a large world like Jupiter, you're probably going to get asteroid belts. We also have the Kuiper belt, which although we don't call an asteroid belt, is really an asteroid belt. It's maybe more ice than rock, but there's still some rocky bodies out there. That really is, some of it is due to a planet like Neptune, again, disrupting some of the formation of a larger body. In fact, one of the reasons Pluto may not be as large and not really a planet is actually due to Neptune and some of its gravitational instabilities that it did. But part of it is also that there just wasn't as much material in the outer part of the solar system, and so it was much harder for material to form. Remember, I think we talked about that part of how planets form is also by their motion as they move around the solar system. And as you're in your outer part of the solar system at 30 plus astronomical units, you're also just moving much slower, and so it's harder to actually accrete more material and build up a larger body. So we think certainly the outer asteroid belts or outer like things like the Kuiper belt are extremely common, and we actually see evidence of that around other stars. We call them debris disks, like the material that's left over from debris of the formation. And we actually see that. That's observed around many other stars. We also see some evidence of some debris in the inner parts of the solar system. I have a student, Chris Dyson, who actually just wrote a paper. You can actually Google it. It's Dyson and West. And he just wrote a paper about observing some warm debris material, so it's from the inner parts of solar systems around really cool stars, that we actually think is not left over from formation like ours is, but is actually the is actually the remnants of collisions of planets. That you actually might get enough terrestrial planets in some systems that they collide, and that what we're seeing is the debris or dust left over from those collisions.
Do we see that through direct detection, or?
We don't see that through, Leanne asked if we see that through direct detection. We don't. We actually see that through excess of infrared emission. So you see the dust, the warm dust actually glowing. And we have no other explanation for how you get that much warm dust, unless it's material that's being produced or, that's really being produced right now in those systems. So.
Okay. Now we're going to take a look at the assessment questions.
Sure.
You want this?
Yeah, there's a couple of questions based on from the assessments that we're going to go over right now. Okay, sweet. So on the few of the assessment questions that we have, I probably won't go through them exactly because I want to make sure that you still have the ability to go and do them yourselves. So I'm not going to give you the answers, but I might give you a few hints and help you set them up. Of course, you also have the ability over the next few weeks to continue asking us questions by posting questions to the discussion forum, and we'll answer those questions if you have specific things that you want, or specific questions or problems that you have with some of the issues. The first is this is from Module 4. I think it's question 15. It's the transit module. And it's question 15, which asks, in 2012, scientists had the opportunity to watch Venus transit in front of the sun. From our perspective here on Earth, it was the last time this would happen for actually over 100 years. And then it asks you to basically make a calculation of how much light was blocked from the sun by Venus passing in front of it. And really in this problem, we want you to have the perspective based on what we've learned that let's imagine you were viewing the sun from another exoplanet, distant exoplanet, at the perfect alignment where you could have watched Venus transit in front of it, and basically ask the question, how much light does that block? And so we want you to treat this just like you would one of the other transiting exoplanet problems, where you have the radius of Venus and the radius of the sun, and what instead you need to calculate is the area of Venus and figure out the fractional area that Venus blocks versus the area of the sun. So it's really just the area of the Venus over the area of the sun. The reason this is could be a little more complicated is actually within our solar system, actually we're close enough to Venus and close enough to the sun that our perspective and our distance from Venus changes. But for the purpose of this problem, we really want you to think like you're observing Venus on a distant exoplanet. And so treat it just like a transiting planet around any type of star. And so you're just literally going to pretend that you're looking at the area of Venus over the area of the sun. That'll tell you just how much light is blocked. And what we ask instead is, how did the brightness of the sun dip down? So it'll really be, you'll subtract that tiny piece of however much Venus blocked. And because Venus is about the same size as the Earth, it should be very close to some of the numbers that we've used in terms of talking about how much light an Earth-sized planet blocks around a sun-like star. If you don't get something that's really close to that, you're probably not on the right path. So I think that's enough information to actually get you started if you're struggling with that problem. And if not, ask us more on the discussion board, and we'll answer more questions.
Tab over. That's from Module 6, I think, the radial velocity.
Okay, I'm going to tab over to the next one. This is, if I can figure out how to work it. Yep. This is Module 6, question 13. And this is, how close would an Earth-mass planet have to be orbiting a solar-like star to be able to be detected by the radial velocity method? Right? Is that the right?
Maybe not.
Oh, Leanne says maybe that's not the right question. We're going to check. Yep, 613. Yep, that was it. So,
yeah, okay.
So if you have one Earth-mass planet orbiting a sun-like star, how close does that have to be in order to measure the radial velocity? So we learned an equation for at least solar mass stars, and we learned about what the mass of the planet was based on the amplitude and the period of a planet going around them. And if I remember correctly, we'll see if I can pull this out of my head. Pull it out somewhere. It was the mass of the planet measured in Jupiter. Can you see that? I think you can see that. Mass of Jupiter, and that was equal to the period over 12 times the amplitude over 13, and this was to the, oh boy, 1/3, I think, if I remember correctly.
Sounds good to me.
Yeah, sounds pretty good to me. And so you have the mass of the planet is equal to some relation. This was for a planet orbiting a star like our sun. All right, that's the key concept here. The period, of course, we know via Kepler's third law. We can express as p squared equals a cubed, again, for a solar mass planet, or solar mass star. if we use units of years and astronomical units. And so, of course, this period can also be expressed really as a distance. If the planet has a shorter period, it's at a closer orbit, and if it's a for a longer period, the planet has a larger orbit. Okay, so part of the problem is understanding that piece of this. Of course, the mass of the planet, we already said we wanted an Earth mass planet. And I think I gave you in the problem that Earth is 1/317th or 318th of a Jupiter mass, so that's what would go here. The other tricky part is what to put for this A, or amplitude. And so I tell you in the problem that our limit right now, although it's getting much better, is 1 meter per second. We have about 1 meter per second precision on radial velocity detection. And so we can actually detect things that are moving in 1 meter per second, which is walking speed. And so it turns out that is the limit, and that's what you should put in there. You would say, like, what is the period I can get that would give me 1 meter per second for an Earth mass planet? So you have to do a little bit of algebra. You have to actually resolve this equation for the period. You need to calculate what's the period for a 1 Earth mass planet that would give you 1 meter per second amplitude. Okay? And then once you have that period, you have the ability to turn that period into a distance. So it's two steps. There's an algebraic step where you solve for p, and you can plug that in and calculate that. And once you get the period, you can now solve for the distance. And you'll actually see that it's, I'll tell you, I won't give you the exact answer. You'll actually see it's fairly close still. That even with the state-of-the-art instruments, we don't have the technological ability to observe an Earth mass planet around a sun-like star. It just does not induce enough of a wobble. It turns out even with the state-of-the-art instruments we saw in the radial velocity module, we went and visited Professor Deborah Fisher's lab at Yale, who is working on the next state-of-the-art instrument that will probably get down to something like 10 centimeters per second radial velocity precision. That, maybe even a few centimeters per second, but probably 10. It turns out that instrument still does not have the precision to get an Earth mass planet around a sun-like star. Turns out you still need something better. But what hers will do is it will get an Earth mass planet in the habitable zone around a low mass star. Because remember, the lower mass stars, it's easier to induce a wobble around. So we are at the point now where technology is starting to be able to detect habitable planets that are Earth-massed around stars, just not stars just like our sun yet. But we're getting there. But it's a huge technological feat to get even to where we are today. This problem just kind of asks you to investigate that and see how much more we have to go.
Okay, somebody just asked a follow-up to the Fourier transform question.
Sure.
They wanted to know if you can use that to separate the radial velocity curve of multiple planets around.
Oh, yeah. So someone just asked a follow-up question on the chat about this is going back to the Fourier transform question, and whether or not you can use Fourier transform mathematics, which remember is this way of detecting periodic signal in things to get multiple planets in a system. The answer, again, in theory, is yes. If you have really strong signals, one of the techniques you can use is to actually look at use this Fourier mathematics to see if there are multiple objects with different periods. And so, of course, you can do that. In reality, again, one of the things that happens is once you've detected one planet, now you're left with, you can subtract actually the signal of that planet out, and what you're left with is new signal, and you can actually do the same procedure again. You can model a bunch of planets, but one technique that is used sometimes, especially if there are really, really clear extra planets, and in some of these exoplanet systems, you can actually see it's very easy just by eye to see that you're looking at multiple planets. You can see something that looks like, I don't know, something like something like this. This would be your periodic signal. And so you see there's one sinusoid that does something like this, and there's another smaller planet on top of that. You have a wobble, we're on a wobble. When I do this in class, I say, if I'm wobbling like in orbit, let's see if I can do it here in my office. You wobble like this, and that's my motion around the balance point, and then I have another wobble like that. So now I'm dancing and wobbling like that, and Leanne is really laughing at me.
An incredible visual on screen.
Leanne's really laughing at me. But I have like a wobble on top of the wobble, and that's what you're seeing there. So there actually are signals where you can see that, and this would be easy. This would easily come out in a Fourier transform. So yeah, we do use that. We use combinations of, again, modeling the data as well as some mathematical tricks like Fourier transform to pull out multiple planets. And Leanne's crying because she's laughing at my dancing.
Okay.
But I hope you enjoyed the Alien Worlds wobble dance.
I certainly did.
Yeah.
All right. So we've got a bit of what they call a wild hypothetical.
Sure.
So they're telling a story about Drake from the Drake
Yeah.
Theorizing using the sun as a gravity telescope, which I assume is a gravitational.
Sure.
And apparently you would need to place your telescope at least 550 AU.
Okay.
So they're asking if that would be, if we could do that, if that would be a good way to look for exoplanets.
So someone was asking about a kind of idea, a hypothetical or theoretical idea, to actually use the sun's gravity as a telescope. It turns out we didn't talk about this a lot. We talked about how gravity bends space, and it turns out that you can do some tricks with that. You can actually lens material from behind the gravitational source. So it turns out we call that gravitational lensing, and it's actually a way of making, of increasing the power of a telescope, if you will, by using objects that will essentially magnify background objects just because of this bending of light. It actually works similarly to the way a real lens would work, using gravity to bend the light and actually magnify it rather than a piece of glass or a lens. So it's actually a very similar technique. It's just using gravity to do so. So someone said, well, we could use the sun, which is our nearest, biggest piece of gravity. You park a telescope at actually several hundred AU, so that would take a while. Remember, Voyager is only about 120, 130 AU from us now. You park a telescope hundreds of AU away, you can now use the sun as a nice gravity lens, and maybe that would help you detect more planets. You would get maybe more magnification, you'd get higher angular resolution potentially, you can maybe do more direct detections. So yes, in theory, that's true. I mean, you'd take, again, a long time to park a telescope that far away, and every time you'd want to switch sources, you'd have to move it a vast distance. So not super practical, but it actually, there's another piece to that that's actually extremely important, and that is that we are not limited in our direct detection of exoplanets by the resolution or magnification of the telescope. If you just did a simple exercise of looking at how well the Hubble Space Telescope resolves objects, turns out Hubble Space Telescope has the angular resolution to observe a planet Earth distance from its star, to actually a pretty far distance, several light years away. So all of the nearest stars, they had a planet that was Earth distance away from it, you could actually have the Hubble Space Telescope has the resolution to see that. Turns out that's not the problem. The problem is that the sun is 10 billion times brighter than the Earth. And so even though the sun can detect that angular distance, the telescope can detect the angular distance. The sun is just so freaking bright that it completely blocks out all of the light from the Earth. And so we are limited by our ability to get the contrast right. We have no device where we can detect something that's 10 billion times brighter than some little dot. That thing that's 10 billion times brighter is always going to wash out all of the signal. And so that actually ends up being our problem. That's why we have to have things like these coronagraphs, which actually Hubble Space Telescope has, that allow us to block out some of that central light and then detect a nearby star. And it turns out the Hubble is not quite technologically great at that to still detect something that's Earth distance away from a star. Just that the coronagraph doesn't do a good enough job of blocking out the light. But again, we're getting much better at that technology. In the next decade or so, I imagine that's one of the exoplanet techniques that's going to most improve, because we are going to have the ability to block that light better and better and see close-in exoplanets, actually detect them in direct detection methods next to very bright stars. Really cool question, though. Really neat. It's 2 o'clock. So I guess we're done with this fourth office hour. Thank you so much for your really wonderful questions. I hope those of you who are watching enjoyed. I look forward to more of your discussion questions over the next few weeks on the discussion forum. And maybe see you again another time. All right, have a great holidays for those who will be celebrating holidays either now or in the next couple of weeks. And enjoy the last segment of Alien Worlds.